Hi, today I'm going to talk about YJIT, Ruby JIT compiler written in Rust. I go by Kokubun on Twitter and GitHub. I joined Shopify last July on the YJIT team. YJIT team develops the JIT compiler called YJIT for optimizing Ruby. And I'm also a Ruby committer maintaining MJIT. MJIT was actually the first JIT compiler merged to CRuby. CRuby is the reference implementation of Ruby. And then second JIT compiler merged to CRuby was YJIT. So this is the main topic I'm going to talk about today. Another Rust-related project I maintain is XRemap. XRemap is a key mapper written in Rust. So if you're a Linux user and also use Rust, then definitely check this out because there are a lot of features in XRemap, and even if you miss something, you can implement that yourself because you're a Rust user. So what's YJIT? So YJIT is developed by Shopify, and as I said, this is the second JIT compiler merged to CRuby. And the reason why I'm talking about this today is because that was originally written in C in the first release of Ruby 3.1, but then in the development of Ruby 3.2 this year, that was fully scratched in Rust. So I think that seems kind of interesting. A part of the motivations we wanted to do this year was because in the first release of YJIT, we only supported x86, the Intel architecture, but because Mark M1 is getting popular these days, we also wanted to support ARM64 so that developers can run YJIT locally as well. So this is the second architecture we are supporting. In this prerequisite I'm showing to you, we developed the intermediate representation, IR for short, to support both x86 and ARM64 without duplicating too much code. Like we only generate IR and then switch the backend to Intel and ARM. So to implement this kind of complicated logic, we were sort of motivated to use Rust. The performance of YJIT is shown here. So we published a website called speedyjit.org. Speedyjit.org shows the latest performance of YJIT. If you generate a Rails application, this almost looks like the code executed by Rails bench. So if you start from a simple Rails project, you should be able to gain this kind of benefit, like a speed up for Rails applications. So like by just turning on YJIT, currently it can just boost your Rails application performance like 30%. So how does YJIT achieve that kind of performance improvements of real-world applications? I'm going to explain how the Ruby interpreter works in general, and then explain how YJIT kicks in to optimize the interpreter behavior. So this is a pretty simple Ruby code. 1 plus 2, obviously that should return 3. So this is a simple method. At first, the interpreter parses the method into a tree called abstract syntax tree. And then because traversing tree could be expensive if you are doing that all the time, we are sort of compiling that into representation called bytecode so that you can just scan the array linearly and instead of traversing pointers to pointers, which is kind of expensive. However, to implement this in a portable manner, we implemented this like a big switch statement that reads the bytecode and then work on that, see this put object token and then put object like a 1 on the stack and push 2 again. So stack has 1 and 2. And then once it reaches up to plus, then it pops 2 tokens like 1 plus 2 and then calculates 1 plus 2 and then pushes the result 3 onto the stack and then leave we return the value 3 from the method. So that's generally how the interpreter works. But to optimize this, we could eliminate, there are some overheads that we could obviously eliminate here, which is bytecode is like read from memory and then interpreted by the switch statement. However, if you have a machine code that does the same thing, we can at least eliminate the overhead of reading this kind of token. We can let the native code do this thing and cache that kind of thing efficiently. And also, if we compile a single method together, we could do more inter-instruction optimization, not just the like per instruction optimization. So that motivates us to implement a JIT compiler. So once we have bytecode and like a method like this 3 is called like 10 times, we trigger JIT compiler to generate a machine code, and then once it's generated, interpreter will just execute the machine code instead of interpreting bytecode from that point. So the first version, Ruby 3.1, like the first version for YJIT was written in C, and that was directly generating x86 64 code. However, to support ARM64, we needed to have the intermediate step that is like, so there's pretty similar code, but like you can see some some indirection like asm sub instead of the directory sub, and like mob is like actual x86 assembly. So like it's a lot different, but I mean that needs to be changed for ARM. So we are sort of generating the intermediate representation like this. So like once we change the code into this, we see some Rust structs like sub and add and jump and move, and so we should be able to translate those intermediate representation into ARM specific code and inter-specific code. So now we are passing through this intermediate step. So we could, instead of generating this inter code, we could generate ARM code as well. And now I'm heading to the topic of lazy block versioning. So we lazily compile basic blocks. Basic block is blocks that are broken whenever you have a branch. So obviously this has a branch like a if branch and else branch, and because we have branches here, we break down this method into 3 basic blocks. So the basic block structure looks like this. The first basic block is here, and then when it reaches the branch instruction, it goes to true case or else case. When we see the first basic block, we only generate the first basic block plus the special code called branch stub. Branch stub is basically just a jump instruction that goes to the implementation of JIT compiler. So like when it reaches this branch stub, it calls the method, the implementation that compiles this code again, and then once it reaches the true close, it triggers the branch stub function, and then that is rewriting the existing code to have more code like get local A and leave. And if we are only reaching this true if true path, we are only compiling this path, and because this is still a stub, we are not compiling this. So this is how we lazily compile a Ruby program. Why do we do this kind of lazy compilation? There are like multiple motivation. The first motivation is a better code locality. By code locality, I mean smaller code. The reason why you want to make the code smaller is because there are multiple layers of CPU caches, and level 1 cache, level 2 cache, level 3 cache. The level 1 cache is actually the smallest but the fastest. So if you want to run code faster, the code should be like fitting in the smallest cache. And the cache, the single block of level 1 cache is called cache line, and cache line is typically 64 bytes. So it's when your code fits in, a code block fits in 64 bytes, your code is likely gonna run faster than larger code. The second reason why lazy compilation is useful is because we could see more time for information out of the lazy compilation. So Ruby is a pretty dynamically typed language. There's no type annotation in the native language design at all. And so if you look at the Ruby method example like this, there's no type information, like the A and B could be actually string. If we lazy compile things, we can see the type information. We are going to look at how that works. So when we execute 3 method 10 times, we trigger JIT compilation of this 3 method. So we compile the first basic block, like A plus B, like this. And then when it reaches opt+, is an instruction that could be optimized further if you know the type of the operands. So if we look at this method, we may not know what type could be the argument of A and B. So what we actually do is like, if we are not at this instruction yet, we call the function called defer compilation, and then defer compilation puts code like this. When it reaches the a plus b, it calls a jump instruction. You can now see the actual arguments. A is, for example, A is 1 and B is 2, and then those are integers. So we could generate integer specific implementation. So like, for example, OptParse could be specialized for int operands. Another interesting concept in YJIT is, I guess, passes. Passes is a concept that is sort of widely used by compilers in general. For example, LLVM, which is also used for Rust as well, usually has the concept called LLVM pass. The way LLVM optimization is called is you generate LLVM IR first, and then IR could be transformed through things called LLVM passes. There are LLVM passes like loop unloading, constant forwarding, register allocation, things that are useful for optimization. So we do code generation first, and then apply the pass called split, and then do the pass during the register allocation. So as you can see, the compile with registers is the main method we are using for emitting native code, and we go. So this compile with registers is called after we do the code generation on the assembler, and then we do the split pass, and then do the register allocation, and then finally we emit the x86 code in this x86 backend. The reason why we have this split pass is because sometimes IR cannot be directly encoded into the machine code. For example, let's say there is a add instruction that adds memory, and then restore that memory, and all of them have some offset calculation. Then that information could be too large to fit into 64 bits. So to encode that, we have to split the instructions into load memory into this register, and load this memory operand into this register, and then load this to register, and then store that to this register, and then load that to memory. That's kind of extreme example, but that kind of thing might be needed for some architecture. So that's why we do this split pass for each architecture. There's also the set of registers could be, of course, different for different architectures. So arc registers is also a different pass for different architectures. So after code gen is executed, the first IR looks like this. So it has a memory operand and like immediate, and it's just a code executed IR generated by CodeGen directly. However, because sometimes we have to split, like this memory operand of sub needs to be loaded to register first, and so we are adding some extra instruction first. You might think it's actually slow, but we are carefully doing this in a way that we are not generating too much instruction. So it's kind of like reverse optimization. We are trying to avoid being slow. So that's kind of how we optimize things here. Then finally, we allocate registers based on the information given by the previous passes. We added inter-specific registers here, and so now this can be easily encoded into the actual machine code. Finally, I'm going to present Rust-specific challenges I've seen in developing YJIT. To interoperate C and Rust, we use BindGen to generate Rust code based on the C headers. So we parse C code using libclang and generate Rust code. However, even while we require Rust to build YJIT, we don't want to add any more dependencies like libclang. To allow users to build YJIT without having libclang, we execute BindGen to generate the code included in the package. So this code right here is the offset between the like, for example, this our offset numiv is the offset between numiv and the head of the struct. So by generating this, Rust can directly access the memory without calling a C function. We can deal with struct generated by C code without going through C implementation. So this is useful, but the trade-off here is the offset could be actually specific to C compilers. For example, ultimately, GCC and Clang could have different offsets, but because Clang tries to be compatible with GCC, at least if you use Clang, it's highly likely that the offset could be the same as GCC generated binary. However, there's another challenge. Obviously, like if you support multiple architectures, the offset could be different between different architectures. At least this obviously different between 64 bits and 32 bits architecture. We currently support only Intel x86 64 and ARM 64, so that's 64 architectures, and that's why we are currently sharing the same code across two different architectures. But when we support 62 bits, it's obvious that we have to generate two different codes and try to avoid sharing that code. Another challenge is the mutable borrow. So like this code is a mutable borrow here, and then this code as well. This code is also the mutable borrow passed to counter exit, and then JIT chain guard has the two mutable borrows of OCB. So we cannot compile this correctly. However, counter exit returns the address of the code, so it's not. Once we call this function, we are not sort of holding the reference to OCB anymore, and like I kind of hope that Rust compiler can automatically sort of figure that out and like just pass the return variable counter exit when JIT chain guard is called. But because that doesn't work, we sometimes ended up defining a local variable that has too broad scope, and because there are kinds of bugs that could be introduced by having unnecessary variables, and if you can just do that without defining variables, then you could have fewer bugs actually. So now that we have the ARM64 support by introducing IR, the next step for us is to introduce CodeGC, because we currently allocate the 256 megabytes first, and then because we currently allocate 266 megabytes and do nothing about extending the buffer or shrinking that when possible. So like it always consumes the same amount of memory, so it's kind of like a challenge for using that on production. So once we implement CodeGC, we could allocate smaller memory first and then extend that as needed later. So that's to make it easier to use that on production. We are targeting that as the next major feature of YJIT. Another thing could be register allocation. As we saw before, we already have the register allocation, but that was for IR operations, not for local variables. So local variables are currently stored on the virtual machines, the Ruby virtual machine stack. But if we also allocate register for storing Ruby's local variables, then that could be even far faster. So that could be the next big target for YJIT. Another thing is method inlining, because Ruby's method code is kind of complex. If we can skip those overhead, then there could be a lot of more performance improvements. Once we have method inlining, we can broaden the scope of optimizations. Like if you have a method call, then that could go to anywhere. But if you inline the method, you can see what's going to be executed in that method call. So you can, for example, constant for these instructions. So you can optimize the code across the method call boundaries once you have method inlining. So in this talk, we saw how the Ruby interpreter works and how YJIT optimizes bytecode into machine code. We also saw the backend architecture. The first goal was to support ARM64, but we also aim for supporting more complicated optimization, which motivated us to rewrite our C-based implementation into Rust, and that has been useful for us to deal with those challenges. Thank you for listening to my talk.